Okay, so my name is Ji-hoon Kim, if you didn't know me yet. So I'm going to present the initial conditions and proof of concept test of the AGORA project, and I apologize if some of the slides are duplicative of what Joel presented already. We should have more carefully coordinated. But I want to mention that this project has come this far only because of the huge effort by many of the AGORA participants, not just me. So I'll do this thank you thing as many times as possible as I go along this slide. So this is just to set the tone of my talk. This is the space of astrophysics code in x-axis, and y-axis is the physics used in each of the simulations. This is the sort of the cartoonic understanding of what I see when I see the numerical simulations of our days. So as a numerical simulator, what you do usually is to set up a suite of simulations, which, for example, one has no feedback and the other has some fancy feedback. And using this suite of simulation, what you argue is that maybe your fancy feedback works to produce a more beautiful, realistic galaxy. So that's probably what you normally do as a simulator. But one of the important principles in any scientific method that people should care about is the requirement of reproducibility. So any simulation, any experiment has to be reproducible by independent-minded people in an independent setup, so that so it can be considered as a scientific knowledge. So as a numerical simulator, what you would do is to set up another simulation using a completely different independent code and compare those two to verify that any success that you've achieved is physical, not by a particular implementation or some weird incident in your simulation. So here comes the initiative that the AGORA project is putting forward. So we want to promote the multi-platform approach to tackle any of the remaining outstanding problems in galaxy formation studies. So to do that, I think 4 of the components has to be emphasized in this AGORA project: common initial conditions, common astrophysics, and the high resolution that can realize those common astrophysics in a reliable manner, and also the common analysis platform to compare apple to apples across different simulations. So in some sense, in this cartoonic figure that I just showed you, what we are trying to do is to carefully and meticulously bracket this comparison with the common initial conditions by music code, as Joel told you, and common analysis scheme by YT code. And we're trying to compare apple to apples, again, fixated in the y-axis of this cartoon using a common astrophysics scheme and the high resolution. So that's what we're trying to do. So I'm just going to describe a little bit about the common cosmological initial condition that we have found, although Joy already mentioned this. But thanks to the music code by Oliver Hahn and Jose Honorbe and myself, we have been able to identify 8 different candidate halos. It takes a lot of feedback process. This whole cycle of identifying the halo can take a lot of time, but thanks to the music code and its expeditious generation of the initial condition, it took only about a few months to identify all the halos and test it. So that's what we did. And this is one of the candidate halos. So what you're seeing is the 10 to the 12 solar mass halo at redshift 0. Also, it's kind of a low resolution test simulation, so you will be slightly disappointed by this figure. But for example, for the proof of concept test that we're going to describe later on, we have a 4096 cubed effective resolution inside the central 2 megaparsec box, which is the Lagrangian region of about the 2 times the virial radius of the target halo at redshift 0. So that's what we figured out as a cosmological initial condition. So And as Joel said, and as I said, we identified 2 merger histories per each mass beam. So here is the violin merger history. So what you're seeing here in the y-axis is the scale factor, and x-axis is the halo mass. And as you can see on this target halo, you can see 3 different major mergers, which is above 1:3 mass ratio. And the other one with a quiescent merger history, you don't see such event occurring. So these are what we basically did along the past year of the project. So I'm now going to describe the proof of concept test, dark matter only test, to verify the infrastructures that we have built so far in the project. So this is the picture that you already saw, but this was using the about 10 to the 11 solar mass halo at redshift 0 quiescent merger history using a 300 parsec resolution run thanks to 9 different code groups who participated. I'm just gonna put a human face on this figure. So a lot of people have stepped up to the plate to do this, take away there, which might have taken away your precious, time and computing time from your career. So this is what we have done. And at the end, what we found is that the structural consistency is really good. The mass difference is within 2% level. And what we found out at the end of this process is that there were no major problems with a single code or 2. So it was mostly a process of trying to configure the right runtime parameters to make one code run compatible with others. So that's what we have done for the past few months or so. And as you might have seen in the paper that Joel mentioned, this is the dark matter density profile, and this is the mass function inside the virial radius of the target halo. And as you can see, the overall agreement is quite good. And I believe this provides a very solid and sound foundation for any of the future hydrodynamics simulation, because we all know that the dark matter only run already agrees very well across the codes. So far it's already good. It already provided a really good foundation for any of the future projects that we plan to do. But I want to emphasize 3 more things that we think we're doing better compared to any of the previous comparison studies. So the first thing that I think is really important is that we're trying to compare the things using a common analysis machinery. So it's not like, for example, in any of the previous studies, what ends up happening is one person, usually the lead author of the paper, just running around to ask each of the code participants to provide me with a processed analysis data, because you don't necessarily know, you're not necessarily the experts on each of all the participating codes, right? So sometimes the code itself is kind of closed to the outside community. So, but what we try to do is take a significant amount of time to develop this machinery so it can be useful for later comparisons. So any comparison that happens later will be made easy because, for example, here is the easy script that you can use to generate this kind of dark matter density or enclosed mass profile, regardless of the simulation outputs that you're using. So all the beauty of this YT common analysis machinery is inside this load function. So this is the data output that you're feeding to YT, and Matt Turk and myself and a few others in working group 4 that Joel mentioned has worked really hard to make this script work, this uniform script work for all the participating codes. in the AGORA project. So it'll work with gadget, gasoline. Of course, this is still a developmental branch, but it's still public. It's public. I just want to mention that we already initiated the AGORA analysis script that is public on Bitbucket. So anybody can download it and test it on your simulation data. And it only has the functionalities at the moment for the dark matter only simulations, and I have tested it for each and every of the 6 participating codes, but yet to be tested for hydrodynamics simulations. So that's where we are at. The second thing that I want to mention is the common initial conditions. As Joel mentioned, and as you probably know from one of Oliver's talks, not in here, but somewhere before, common initial conditions are made easy and easy to transferable. The common initial conditions that the AGORA project is providing is really easy to transfer, easy to be transferred, because all you need is the parameter file, not the binary file that can be really heavy to transport. So it's already open for business, and people are already starting to use. So previously, the reproducibility of the numerical experiment was not necessarily guaranteed by the simulators of the article. So it has to be, if you want to reproduce some kind of simulation, you have to ask the people to provide you with the initial condition. Whereas what we are trying to do here is that cosmological initial conditions are already open for business on the project workspace, and you can always join it without any obligation. So it's not completely fully public, but you can download it if you want. And as you might have seen in Phil Hawkins's talk yesterday, it's already starting to be used in the independent individual researches. And I know that many other people have already started working on the AGORA initial conditions for individual projects. So for example, here this is my example. So I'm working with Mark Krumholtz and others to simulate the quasar hosting galaxy at around redshift 7, and this is actually the progenitor of the 10 to the 13 solar mass galaxy at redshift 3. So this will be a simulation including the radiative transfer by the individual star particles, which represents about less than 1,000 solar mass. I'll probably perform a full radiative transfer simulation for about 50 million years, so that to study the morphology and evolution of the quasar hosting galaxy. So this is just one example. So even though you don't intend to do any comparison study when you start this kind of individual research, because you're already building some kind of AGORA simulation library, you can easily compare this simulation with any subsequent simulation using like the common analysis script that I just described. So it'll be really beneficial for the entire numerical simulation community. The third thing that I'll just only briefly mention is that this whole project infrastructure doesn't get lost when we publish 1 or 2 papers. So what happened before is that, as Joel mentioned, all the work that you have done, you have put forward for making this project work gets lost once the paper is out. And I just went back to my mailbox and checked how many emails I sent regarding the AGORA project, and I realized that it's more than like 1,500 or so. And that I know that effort is not going to be lost after we published this flagship paper. We are pretty sure that a lot of people described here will be really geared off for the science-oriented projects and subsequent projects over the course of the workshop over this weekend. So I'm really excited about this. I'm really happy to help this project to be propelled to the next phase. So that's, I think, what I prepared. And I just want to mention that we are in some sense at a critical junction in the numerical, in the development of the numerical techniques to understand the galaxy formation. And I hope you join this effort, and yeah, I really hope we can do something better out of this. Thank you very much.
Thank you for being almost perfectly
Yes.
on time. That was uncanny. All right, so we have time for questions. Everybody's completely satisfied with AGORA? Oh, yeah, Santa.
Make a recommendation for people to come back or go and be simulated again? What's the situation?
Yes, I mean, Joel is smiling. You want to answer this?
Well, actually, Oliver's here, I think.
Yes.
I think the plan is that there's going to be a follow-on paper that
Yes.
analyzes the outputs from the code with the command parsec and also parsec resolution of concept runs with just dark matter. And we'll try to understand, I mean, as I said, and in more detail as Ji-hoon said, we're pretty happy with how well the codes did. It could have been a lot worse. But of course we want to understand, the systematic differences, for example, in the subhalo mass functions, and maybe improve the code so that they all do a better job, or at least the ones that aren't doing as well do a better. And that'll be the focus of this paper that looks at generating the initial conditions and what the effects are, at least in these dissipationless runs.
Right. So during the weekend sessions, we're going to have a breakout discussions like Oliver, myself, Annalisa, Filippetti, and Shijing. We're going to all discuss how to even more carefully analyze this dark matter only simulation using, for example, the Rockstar Halo Finder, which wasn't unfortunately included in this proof of concept paper. So we're going to, clearly do more effort on that front.
One thing that really encourages me about AGORA versus previous stuff is that there's always been a gotcha element in previous comparisons. Like with the Santa Barbara comparison, they wouldn't even let people see what their stuff looked like. And there was a couple of codes, gotcha, it looks like crap, but we didn't learn anything from that. It was just chess speed. And even in Aquila, the real what actually exploded wasn't so much a gotcha, but it was just they found differences and then it stopped. And what I really like about AGORA is their continuing conversation. The idea that it's not a terminal project, people actually learn where the differences come from.
So we need to talk with the tool how to improve the quality. But what we do, we go and tell people how to fix it.
Well, we don't know anything.
What?
We don't know anything.
All right,
Because we are.
one more short question. Yes.
Can you update us on the status of Rockstar, or somebody else was doing it?
I have asked Peter Burzy to join in the remote discussion, so I hope he does. Yeah, I mean, that's the status.